Let me make sure it's up and popping. So, okay, it's saying it's coming up, y'all. Y'all see this? It's making a connection. Whoop. Okay. So let me go ahead and share my screen on YouTube. Okay, there we go. All right, so it's up. We're popping now on YouTube. Okay, so let me make sure. And there may be a delay, but we are there. Okay, we are there. Okay, so as you guys can see, okay, there we go. So yeah, we're good. Okay, we're good now. All right. So now you all don't have to ask me, is this gonna be recorded? Yes, it's up now on those YouTube streets. Okay, so let's get back into our lesson now on Lewis dot diagrams. All right, we're good to go now. So with Lewis dot diagrams, you've got to have access to a periodic table. Your periodic table will tell you all you need to know about this. Now I put up some quick notes that says valence electrons equals the outer shell. It also equals the number of electrons to draw on the element to form the bond. Now, what does all this mean? I'm going to tell you, okay? I'm going to visually show you what this means. So now, Asia, I know you requested this particular unit, so I'm going to make sure that you get the information that you need for this. If you have questions, honey, let me know, all right? So I can make sure I answer and address your concerns, okay? Hey, Tristan, you need to know the valence electrons, right? Like oxygen. That's correct. You need to know the valence electrons, okay? Because here's the deal. The valence electrons will tell you how to draw the picture, okay? Now, this, let me tell y'all, ain't nothing to this but to do it, okay? Ain't nothing to it but to do it. So here's what I mean by that. I'm going to keep this here. I'm going to write on here things that you need to know, okay? So when it comes to valence electrons, the group numbers tells you everything. So if we look at group 1, there's 1 valence electron. Group 2, there's 2 valence electrons. We skip groups 3 through 12, and then we get to groups 13 through 18. We drop the 1, and then that tells you the number of valence electrons that it will have, okay? 8 is the lucky number. 8 is the ideal number when it comes to valence electrons because all the elements are trying to acquire 8 in order to make it happy. So now y'all know I'm going to use headline stories to explain this in further detail. If you think about the elements or the famous people, these celebrities, for the most part, most of the celebrities are like the group 18, where they are above everybody, or so they think until they get humbled. So when you get to group 18, those are the numbers that you want to have for your element. Now, when you look at the valence electrons, it goes from 1 to 8. 8 is a complete shell. 8 is full. So here is the thing, though, even having said that, if I give you an element, yep, that's right. They're always full because they are noble gases. That is correct. So if I tell you to give me the Lewis dot diagram for, let's say, hydrogen, well, guess what? Hydrogen is in group 1. It's right here. Because it's group 1 element, guess what? We're only going to draw one little dot. That's it. That's it. Now, let's mosey on over here to group 15, right? Group 15, we're going to pick an element. Let's pick phosphorus. Phosphorus is in group 15, which means it has 5 valence electrons. So you know what we're going to do? We're going to put 5 dots around it, and they come either solo or in pairs. So it's going to be 1, 2, 3, 4, 5. Okay, there is no right or wrong in how you put the dots on there in terms of, I could have drawn it like this. I could have had 2 together over here, 2 together right there, and then 1 at the very top. It doesn't matter as long as they're either individual or as a pair, but you would never put 3 together, okay? You would never put 3 together. Now, Okay, for example, NH4 plus ion, 5 valence electrons for nitrogen, 4 valence electrons for hydrogen, -1 for the cation. Oh, honey, you on point. Let's draw that one out, Asia. Yeah, let's draw that one out. So the request came in for NH4, okay? So if you know about the group numbers and how they indicate the valence electrons, honey, that's half the battle. So you've got NH4 with the +1 charge. Okay, well, let me show you how to draw it out. Okay, you've got nitrogen, like you said. Nitrogen you only have one nitrogen, so that's the one there, times it's in group 15, so it's going to give 5 valence electrons. You've got your 4 hydrogens, and it's in group 1, like we said before, so that's times 1 to give you 4 valence electrons. Now, you're going to add those together, and you're going to get 9, yes, but here is the deal. You get 9, but because of that +1 charge up here, we're going to actually subtract 1. When in chemistry, when it's positive, we subtract. When it's negative, we add. Now, I'm going to show you the easiest way to draw this out. The easiest way. Puffy and all these low vibrational celebrities, they over here, they want to rob, steal, take that from the people that are supposed to be helping them get to the top. So because he's in the middle, we're going to call him nitrogen. Because he's nitrogen, okay, he's only coming in with 5 contributions. Okay, so watch this. You're going to get it after I show you this. Nitrogen, aka Puffy, he's going to go right there in the middle with 5. But he's like, look, I know I'm only going to give y'all 5 contract deals, but you need to give up something too. So when hydrogen comes in, hydrogen is going to say, all right, let me give you 1 of me. The other hydrogen says, all right, I'm going to give you 1 of me. The third hydrogen comes in and says, yep, I'm going to give you 1 of me. And then the last hydrogen is going to come in. Now, even though this last hydrogen that came in isn't giving up anything, you are going to count these dots around the middle. Puffy, aka, is the middle element. He has to be surrounded by 8 valence electrons. In order to make him feel good about himself and to be satisfied, you've got to make sure that the middle element and any element from groups 14, 15, 16, and 17, they have to have 8. So in this case right here, the one in the middle has 8, but here's what you got to remember. You're going to redraw this because we're not done with this yet. You're going to redraw it, put Puffy in the middle, aka nitrogen, redraw those little dots with dashes. You're going to replace them with dashes, okay? And then in brackets, we're going to put that +1 on the outside. And that +1 came from the formula NH4 with the +1 charge up here. So that positive charge, or if it was negative, it would have to go on the outside in brackets. Okay, it would have to go on the outside in brackets. Okay. We got to do another one because we want to make sure we are totally getting all of this. Okay, we're going to do another one. So suppose we have, Asia, give me another one. What else you got? Because I can pick one, but I want you to give me one too. So why didn't you add the last hydrogen? I'm confused. Why didn't you have to give it up? Oh, good question. See this number right here? We had 9, right? But we had to take away 1. So you can kind of say that Puffy robbed hydrogen of 1 extra, okay? And to account for that extra one, this total number here that you have, the 8, you have to make sure that the total number here equals the dots that you have right there. So all this has to equal up, right? It has to balance, right? To balance it. That is correct. To balance it. And that's how you account for that extra one. And I know, okay, PCl4 with the +1 charge. All right, let's do that one. Okay, so let's scroll this down. Okay, so we got PCl4 with a +1 charge. Okay, so you've got phosphorus, chlorine. You've got 1 phosphorus, but you've got 4 chlorines. Now, again, I know that phosphorus, let's go ahead and pull the periodic table back down so we can look at that to refer back to. We know that phosphorus is right here in group 15. Chlorine is in group 17. So phosphorus is going to give up 5, and each of the chlorines is going to give up 7. Okay, so right here, phosphorus is giving up 5 valence electrons. So 1 times 5 gives me 5. And then each of the chlorines is giving up 7. 4 times 7 is 28. So now 28 plus 5, that gives us 33. Now, in chemistry, when we're doing Lewis structure, Lewis dot diagrams, VSEPR, you never want to have an odd number, because if you do, that means we got some free radicals going on, and we don't want free radicals. Free radicals equals a mess. Free radicals equals an issue. Free radicals equals, nah, we don't want that, okay? It equals problems. So remember how we said we have this positive charge up here, right? In chemistry, correct, we should have 16 pairs. Okay, well, we're going to get to that part too. Because it's positive, we need to do what? Subtract 1. So that's going to give us 32 valence electrons. Yes, you are right, Asia, to say 16 pairs. Let's figure out how they're going to match up in the picture. So Puffy, remember, the one that goes in the middle, they have to have 8. But we're going to start off with what Puffy, aka phosphorus, is giving us, okay? So in this case right here, phosphorus is giving up 5. So we're going to go ahead and draw those 5 dots around it. So that's 1, 2, 3, 4, 5. Now check this out. Chlorine is kind of like 50 cents. Okay, chlorine is like, yo, I need my electrons too. So in other words, when we bring in 7, because each of those chlorines is going to contribute 7, watch this. 1, 2, 3, 4, 5, 6. Puppy said, well, give me one of yours. That makes 7. Here comes the next chlorine. 1, 2, 3, 4, 5, 6. Here comes the next 7 right there. There's a 7. Here comes the 4th chlorine. 1, 2, 3, 4, 5, 6, and then 7. And now here comes the last chlorine. 1, 2, 3, 4, 5, 6. What happened to the 7th one? Remember, this negative charge, or it wasn't a negative charge, it was a positive charge. We had to take away that 1 right here. See that positive 1 at the very top? That one right there. We have to take that away. So we don't add it to it. We got to take it away to balance it out. Like K24 said, we got to balance it out. Okay? Now, because of space, I'm just going to erase those little dots. But before I erase the dots, let's make sure that all those dots that we just wrote, it's got to equal to 32. Let's count them to make sure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And voila, we are done. Kind of. What we got to do, we got to go ahead and replace the dots that were circling around phosphorus. Just replace those with a dash. Okay? So I'm just going to erase them. But also, let me tell you why even the chlorines have to have 8. Because they're all striving for the same level of attention. You know, 50 Cent ain't gonna go without being petty and getting attention. So even 50, like all 50 and Puffy, they're both striving for that same attention. So you got to make sure that they all have 8. Okay, that's why you got to make sure of that. And I'm gonna show you one with the double bond, so you can see what I mean about that. Okay, because all of this makes sense once you put them together. So I'm just deleting the yellow lines around it. Now we got to put this entire thing in brackets and put on the outside, put on the outside that +1 charge. And that's going to let us know that there was an extra valence electron that we had to deduct away from it. Okay? That's what we're doing right there. Now, I'm going to do one that deals with, and then I'm going to get to the electron configuration question, okay? So, this right here, what you just did, it'll all make sense as you practice them, because you also have to know how to determine their shapes, okay? You got to know how to determine their shapes as well. And it's all based on what's happening to the elements in the middle. Now, let me do one like this where you've got a double bond, okay? Or let's do a triple bond. HCN, aka hydrogen cyanide. Hydrogen cyanide. Okay, double and triple. Yeah, honey. You know what? As the young folks say, say less, I got you. Okay? So you've got hydrogen, carbon, and nitrogen. Let me tell you, there are 3 major elements that can form double and triple bonds. Okay? There are 3 of them that typically will do this. Double and triple bonds, carbon, nitrogen, and oxygen. Those are the 3 that gets down with kaboom, okay? They typically do the double and triple bonds. Double and triple bonds means they're very unstable, okay? They're very unstable. And because they're unstable, that's where the double and triple bonds come from. Now, as I draw this out, I want you to watch how I do so that you'll know how to go back through them again. And y'all, this is on my YouTube channel as we are speaking right now. I am live right now on YouTube. So if you all want to see the replay, you can go on over there and catch it. Okay. Now, what I'm going to do, I'm going to put 1 hydrogen, 1 carbon, 1 nitrogen times their respective numbers of valence electrons. Hydrogen has 1 valence electron because it's in group 1. Carbon has 4 valence electrons because it's in group 14. And nitrogen has 5 valence electrons because it's in group 15. We're going to add all those together and we get 10 valence electrons. Now, what's going to happen? You see the way it's written, HCN. That's the order you're going to write your bonds or write your structure. So I'm going to put 4 right here for carbon. I'm going to go ahead and put hydrogen right here on the left, but I'm going to put the extra one right there on the top. I'm going to put nitrogen right here on the right, plus 5. Watch this. 1, 2, 3, 4, 5. Now, I'm going to zoom in on here so you can see what's getting ready to take place. Remember how I told you, any element in groups 14 through 17, they must have 8. They're all striving for the same level of attention. Hydrogen could give 2 blanks, okay? They could give 2 Fs to give, okay? They don't care about having a double bond, triple bond, none of that. They're all going to make that one relationship and they move on. So as you can see, hydrogen gave up 1. Yes, that's right, Asia. The one that is the most electronegative must go in the middle. So you notice celebrities are like the most electronegative elements. So fluorine, that's the most electronegative element. So I'm going to scroll back down to the periodic table. Those that are over here, as you get closer to the right side of your periodic table, they become the most toxic element, okay? I'm like you, K24. I'm hydrogen too. I don't care about being the center of attention, okay? So why wouldn't nitrogen be in this case? Oh, honey, it is. It's that case. Let me tell you why. Only one of them can be in the middle. but they both gonna struggle for that attention. So they both gonna have 8, and that's where the double bonds and triple bonds come in. You're not gonna be the only one with the mic. I'm gonna get that mic too. Hence, both of them having the same number of electrons. And so here's what happens. You see these two right here that are by themselves, one and that one? Guess what? They both got to give it up. And the only way they're going to be able to give it up is by putting them in the middle. So again, if I got to give it up, you're going to have to give it up too. That's what they're both saying. So in order for them to work, we're going to erase those two and pull them right there in the middle. See that? So now they're sort of happy. Let's count how many valence electrons nitrogen has. 2, 4, 6, 8. Nitrogen's like, all right, bet. I got my 8. Carbon, what you got? Carbon said, all right, let me see. Let me count. Let me see. Carbon says, I have 2, 4, 6. Carbon is complaining. Carbon said, wait a minute, you're not going to be the only one shining. I'm going to get my 8 too. So where we're going to get the extra 2 from? Nitrogen is going to have to move these 2 from the top right there to the middle. And now carbon's like, all right, we equal now. So basically, this is where that triple bond comes into play. So carbon and nitrogen are sharing those valence electrons. And if you count those dots, you're going to end up with 2, 4, 6, 8, 10 around this structure. To draw this picture out, it's going to look like this. And there you have it. You have a triple bond between carbon and nitrogen because they both saying, you know what? You're not going to be the only one with 8. I need my 8 too. And this is what you got. Asia, does this make sense? Don't be saying, sure, honey. If it don't, honey, let me know. Let me know. Look, listen. If it's not making sense to you, if it's not making you think, yes, I can do it by myself, then you need to say something, okay? Okay, OCN with the negative charge. Okay. Lydia says, how do you know when you need to add another bond or have the unshared electrons on top? You're talking about this one right here, the unpaired right here? You mean like, do I put them on the top or the left or the bottom? Is that what you're asking, Lydia? Oh, okay. So you can put them on the top if you want to. You can put them on the bottom. That part doesn't matter. You can put them anywhere on nitrogen, the right side, the top side, or the bottom side. That part doesn't matter. Okay. We're gonna do this one, this OCN, but this time, Asia, I'm gonna let you help me out, okay? I'm gonna let you walk me through what we should do right here, okay? So we got OCN with the negative charge. Okay. Oxygen, carbon, nitrogen. Again, Asia, let me ask you this. You know how to do this part, right? This is counting the total number of valence electrons. You know how to do this part, right? Okay, like I told you, this is half the battle then. Okay, so let's add these up. We got 15. But remember, because of that -1 right here at the very top, we're going to add 1. Okay, good. So yes, 16 electrons, 8 pairs. Yes. But here's the thing though. Even though you say 8 pairs, there may be some double bonds and triple bonds in there. Okay. So again, the structure was OCN with a negative charge. Yes, it's the drawing. So let's draw this together. Okay. You can actually start with oxygen. I always just like to start it with the one in the middle, just because, I mean, that's the way it's going to look anyway. So you've got 2, 4 for carbon. Okay, again, if we go back up here, and I'm gonna zoom out a little so you can see this part right here. So if we go back to our picture right here, and you notice how carbon comes in with 4, that's where the 4 dots come from for the carbon right here in the middle. Now we're gonna go ahead and pull oxygen right here, and it's gonna contribute 6. So I'm gonna put them on the top, 2, 4, and 6. Okay, now we've got oxygen out the way. Next up, nitrogen. So here's nitrogen with how many, Asia? How many is nitrogen going to give? Very good. 5. So that's 2, 4, and 5. Now, here is the deal. Each of these elements here, oxygen, carbon, and nitrogen, all 3 of them need 8. Here's why. Let me refresh y'all's memory again. They all need 8 because this is as far as I got. Okay, that's good. Not a problem. Remember, from group 14 on, okay, I'm going to put this up here on the board so y'all can see that. Groups 14 through 17, any element that's in that group, they all need 8. So that means whatever element that's coming into that relationship with those elements, they're going to have to give up their electrons to make sure that any of those elements that's part of 14 through 17 to get 8. So in this case right here, that means they're going to have to be sharing. So if I scroll back down here to this structure, you got to, oh, and remember, there was an extra one that we have to account for. Remember that? So we can't forget about the extra one. Because, and matter of fact, let's count. We've got 2, 4, 6, 8, 10, 12, 14. That's 15. We can't forget about the 16th one. So we got to go back in there and put that on. Okay, so I'm going to go ahead and put that back on. I'm just removing the blue light first. Okay, and I'm going to add this extra one right there. Now, here is the deal. Oxygen has 8. Watch this. 2, 4, 6, 8. So oxygen is like, oh, I'm good. Nitrogen has 2, 4, 6, 8. So nitrogen is like, oh, I'm good too. I got 8 too. Which one of these elements is complaining and why? Which element is complaining and why? Okay, Asia, why is carbon complaining? Okay, yes, Lydia is correct because it has 4. Where is it going to get the 4 from? Double bonds, yep. Chrissy said nitrogen. Okay, users 7633 said oxygen and nitrogen. Y'all are on point. Y'all are on point. I had accidentally erased that one, y'all. Okay, that is correct. So here is the deal. I'm going to erase. Watch how I do this. I'm going to erase these 2 right here that were on the top of nitrogen, and I'm going to put them right there. See that? That's 2, 4, 6, 8. Nitrogen still has 8. Carbon is like, okay, nitrogen, you gave me 2. What's up, oxygen? I need my 8 from you too. So guess what we're going to do? We're going to take these 2 from the top of oxygen and put them right there with carbon. Now, look at your picture. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. And now everybody can now be happy. Okay? But I'm going to redraw this picture so that you can see that, the clean version. So would it be pairs around oxygen and nitrogen, then 2 lines on each side? Yes, very good. So that's what I'm going to do now. I'm going to redraw this bond here so you can see that. And again, and remember, you got to put this in brackets to show that we had to add an extra one. Remember. I could have put my dots up here, y'all. That it doesn't matter where you put them, as long as you put them there, okay? So you could put them on the top, on the side. So like this, I could put 2 right here on the top of oxygen and the 2 on the bottom. That doesn't matter as long as you're giving what this element, this compound needs. Okay. All right. So, Asia, you good to go? Like, is this making more and more sense now? Okay. Excellent. Excellent. Hey, Christy. No, honey, I don't do organic. I do not do organic. But if you DM me, I can tell you whose accounts that do. Okay. So now I know we had another request. So let me let me look at the next thing that was on the list. You're welcome, no problem. No problem. Electron configuration. The person that asked about electron configurations, are you still here? The person that asked about electron configuration, are you still here? Okay, good. Okay, so now we're going to transition to electron configuration, okay? And let me pull up some stuff here. Hold on, let me see. Electron configuration. Okay. So now, so that you don't see these answers right here. Okay, yeah, this is what I can do for you right here. Okay. So I'm going to, let me see if I can copy this and take it to the other screen that I was on. Okay. Okay, here we go. Electron configuration. Now, I previously did an example like this from before, and what I'm going to do is show you how all this stuff makes sense in terms of electron configuration. And listen, electron configuration is not difficult. Matter of fact, I have some worksheets that you could actually get on this. Let me erase some of this right here. Matter of fact, I'm gonna rewrite that part over. Okay, so here's what you need to know about electron configuration. And I'll explain about the worksheets in a minute. But with electronic configurations, you have to know about the energy levels and the blocks, okay? Matter of fact, let me show you this real quick. This was one of the worksheets. I gotta, hold on, y'all. Okay, with electron configuration, it is based upon energy levels and the number of electrons. I think I got, Yeah, hold on. Okay. Well, yeah, this is one of the examples right here for electron configuration, one of my documents. And I know YouTube, y'all can't see this just yet, but this is one of the worksheets that I was working on right here. Matter of fact, hold on. I'm gonna make this, let me I'm going to download this in a PDF so that I can share this on the screen. Okay. So that I can share this on the screen. I'm going to download this as a PDF. So, and I'm going to also share this with YouTube so that YouTube can see this as well. Because I actually have some notes on this document that you can actually pull from so that you can see it. Okay. So let me, okay. There we go. So this is one of the worksheets that I have. YouTube, y'all hold on a second. Let me go ahead and pull this over for y'all. Okay, here we go. All right. Now, for electronic configuration, this is one of the documents that I have right here. This is something that you can actually get, and I'll have this available for you, for purchase. But right here, when it comes to electronic configuration, there are certain orders that you have to follow. Okay, so when it comes to electronic configuration, you want to make sure that you're able to know how many electrons goes in each block. So when you look at the S block of elements, the S block has 2, okay? That's like your first 2 groups. Skip groups 3 through 12, but when you get to groups 13 through 18, those have the P block elements, and they have 18. The D blocks, that's in the middle. They actually will get 10. You have a maximum number of 10. And then the F blocks, you actually have 14. Now, here is the deal, though. Based on what I just said, the maximum number of electrons you get for each of those energy levels, I always tell my students to make sure that you are not going to exceed the maximum number of amounts. So if I told you to write the electronic configuration for a given element, let me give you one so that you'll know what I'm talking about. This is the order that you have to follow right here. You got to start off with 1S, then you go to 2S, then 2P, then 3S, 3P, 3D, and so forth. This is an order that you go through, okay? It looks like this in many of your chemistry books, but this is the order that you have to follow in order to fill them up. So if I give you an example to do, okay? Because there are some exceptions to the rules. But let's do one to practice so you know what I'm talking about. In order to do electronic configuration, you've got to first determine how many electrons does the element have, what block is the element located in, and what energy level is the element located in, okay? That's important. And we're going to do one together so you can see what I'm talking about, okay? We're going to do one together. So let's do oxygen, okay? We're going to do oxygen. So, and I'll show you the answer in a second. Okay, so we're going to do oxygen right here. Oxygen is in group 16, okay? And remember how we were talking earlier about valence electrons? You're going to see how all of this makes sense. Oxygen, if we zoom into oxygen, how many electrons, not valence, but how many electrons does oxygen have? Oxygen has 8 electrons, right? Okay, keep that in mind. Oxygen has 8 electrons. Okay, because it has 8 electrons, what you have to remember is that there is a certain thing you have to know. It has 8 electrons, and because it has 8, you also need to tell me, well, what period is it in? Okay, period means the energy levels, okay? Let me show you that too, right here. See, oxygen is right there. It's in period 2. See that? If you go straight across, it's in period 2. So we're going to write that down also. It's in period 2. Now, what block is it in? It's in the P block. Which one? 1, 2, 3, 4. It's in the 4th one. All this is going to make sense as soon as I put this together, okay? Here it is right here. It was in the P block. It was in the 4th one. Guess what? This is going to be the last thing that you write down for oxygen's electronic configuration. You're going to write 1s2, 2s2, 2p4. You see this right here? 4 plus 2 plus 2 gives you 8 electrons. That's the number that you have to have for oxygen. Now, what valence electron number does oxygen have? It has 6. See that? Because it's in group 16, because it has 6 valence electrons, that's the total number that you're going to write on the last energy level. That second energy level is going to get a total of 6. That's where the valence electrons comes into play. See what I mean, guys? All of this with chemistry, it comes full circle in terms of understanding how what you learned in one chapter comes back in another chapter in a different way. Okay? That's what this means. So when you're doing valence electrons and writing out the electron configuration, you have to know these things right here. How many electrons does it have? What period is it in? What block is it in? When you know all of those things, that tells you everything you need to know to write this out, okay? Now, let me do another example so you can see this. Okay, I'm gonna do another one. I'm gonna copy one of my questions right here so you all can see this too, okay? Because the thing is, as we say, practice makes perfect. Yes, that is true. But you got to kind of look at everything as a pattern, okay? Look at everything as a pattern. Here's one of the questions right here. Okay, we're going to look at question number 1. Question number 1. What is the electron configuration of an element with 6 valence electrons? 6 valence electrons. Now, here is the deal. To understand what that question is asking you, you've got to look at the last energy level, and that's going to tell you that. So let me zoom in so y'all can see this, okay? I'm going to make it a little bit bigger. Yes, we're doing, Monique, yep, we're doing this step by step. Yep. Okay. Here's what they're asking. Because we were asking about the valence electrons, okay? If you notice anything that has 6 valence electrons, let me go back up here because I'm a visual person and I want y'all to be able to see what I'm talking about, okay? I'm gonna zoom in so you can see that. Yes, Monique, I'm glad. Yeah, okay, you're studying for the MCAT, okay? And you're gonna have to know this for chemistry, the chemistry part, yes. Okay, so you see this, right? You see 6 valence electrons. What block are those elements that have 6 valence electrons? It's in the P block, right? I want y'all to take a deep breath as we go through this. Okay, good job, Monique, good job. Okay, so you just told me it's in the P block, right? This is how you all do process of elimination when it comes to your answer choices. So I'm gonna zoom in so y'all can see this. Which one of these elements is in the P block for the last thing that is writing for 6 valence electrons? So here's how you know. The last energy level, the last energy level, the last energy level, the last energy level. Which one of those adds up to 6? Okay, good. Monique said A and C. Bara said A. Monique's, okay. Monique is saying A or C. All right, here is the catch. Here's how you're going to know this. What is 2 plus 2? What's 2 plus 2? That's equal to 4. So we know it's not letter C. So we know it's not letter C. We know it's not letter D because it says 6 valence electrons. 6 valence electrons is over there in group 16. So we know it's not letter D either. So it's between A and B. But listen, because it says 6 valence electrons, it has to be letter A because guess what? 6 valence electrons is in the P block. So the answer is letter A. Okay. Good job, guys. Y'all are doing good. I'm glad y'all have patience to listen to this. Because see, guys, I mean, you got to hear the backstory in order to appreciate where all this is going. Let me give you another practice problem. Hold on, y'all. Okay, let me zoom out so y'all can see this. You're welcome, Vara. You're welcome. Okay, take a look at question number 2. For the element with the electron configuration 1s2, 2s2, 2p6, 3s2, 3p1, what is its group number in the periodic table? Group number, what is it? Here is an easy way to think about it. Yep, you do got to read it, yes. But they're asking you, what's the group number? Okay, here's how you determine that. If you look at actually, there are 2 different ways we can do it, okay? You can easily add up these superscript numbers. What's 1? Well, let's start here. 2 plus 2 plus 6 is 10. Plus 2 is 12. Plus 1 is 13. So because I added up those little superscripts, that 13 tells me 13 electrons, right? But it also tells me drop the 1, and that gives me 3 valence electrons. And it also tells me group A. How do I know that? Because on the last energy level, 2 plus 1 gives me 3. 2 plus 1 gives me 3. 3 means group 13. Okay. Yes, Monique, I sure can. Yes. So here's the periodic table right here. And I'm going to zoom in. If you added up those numbers where it's told you 13, like when we add up those superscript numbers and it says 13, aluminum right here has 13 electrons. Aluminum is in group 13 also. There are 13 people in this group, in this live right now. Can we say 13 isn't a bad number? Okay. Last week was Friday the 13th. Well, actually, 2 weeks ago. Yes, 13 would be the total number of electrons for the element. That is correct. That is correct. And it just so happened to be that it was in group 13. Yes. Okay. So now, we got to do another one just to make sure. When you count all the superscripts, no matter what, it's going to give the electrons for a specific element. That is correct. Correct, correct, correct. Yes. You are on point. That is correct. Okay, take a look at this one right here. Write it out. Alyssa, you got it. You got it. Okay, so guess what I'm going to do? Let me cover up the answers right here. Okay. Now look, I can't. Okay, there we go. We covered up the answers, right? So I'm going to zoom in on this piece right here. Matter of fact, we're not going to even look at that part. I'm just going to give you chlorine. Okay, we got chlorine. First thing we need to do is figure out how many electrons does chlorine have. Chlorine has 17 electrons. And if we look at our periodic table, chlorine, matter of fact, let's pull up the periodic table. Let's scroll back over here. Here we go. Chlorine is in what group? If you take a look, it's in what group? It's in group 17, which means you drop the one and it's going to tell you, right, it's going to have 7 valence electrons, right, on the outer shell. Now, here's the next question. What block is chlorine? What block is chlorine in? Good job. Good job. Excellent. It's in the P block. Which one? Let's count over. 1, 2, 3, 4. It's in the 5th one. P5. It's in the P block. It's in the 5th one of the P block. That's what we're going to write for the last thing. So let me go back over here. It's in the 5th one of the P block, but we're not done. What energy level? What period? That's what we mean. When we say energy level, that means period. What period is chlorine in? So here's chlorine. What period is it in? The first one, second, third, fourth, fifth, sixth, seventh. Which one is it in? Very good. Alyssa, good job. It is in the 3rd one. So guess what? Hi, how did you get 7? It's not in the 7th period. It's in the 3rd one. So 3p5 is the last thing that we're going to write for our electronic configuration, okay? And because that is the last thing that we're going to write, we're going to say 1s2, 2s2, 2p6, 3s2, 3p5. That's it. That's the, now listen, another thing that I've done, I tell my students, if you just memorize, if you memorize the electronic configuration, 1s2, 2s2, I'm going to write this out so you can see what I'm talking about. This is another thing that will help you. Okay, I'm going to stop right there so you can see this, okay? Okay, my question is, how do you know the number before the P? Oh, honey, good question, good question. You're talking about how did I know to write 3p5? Is that what you're asking, Alyssa? Okay, good question. Good question. So if you go, okay, so those of you all that are doing electronic configuration, let me share this screen also with yeah, there we go. All right, right here. When we talk about electronic configuration, there is an order that you have to follow, okay? There is an order that you have to follow. You see this guide right here where it says 1S, 2S, 2P, 3. This is what you see in chemistry books, but this is the order that you must drive the bus, so to speak, drive your car. You got to go in this order. Fill up 1S, fill up 2S, 2P, 3S, 3P, 4S, 3D, and so forth. This is the pattern that you go by. I tell my students, though, that when you're writing this down, I'm gonna show you something real quick. I'm gonna show you how to address that concern. Okay, let me copy this out so you can pick up what I'm putting down. Okay, I'm gonna take one of these that's already written out because then you're gonna say, yeah, hey Juju, yes, I will have this document available for purchase in my membership, so you will be able to get access to this. Yes. Let me go right here. Okay, so if you memorize this electronic configuration right here, okay. Let me make that bigger so y'all can see this. This right here, this goes up to number 20, okay? Y'all see this, right? You're welcome, Juju, you're welcome. You see this right here, right? Let me enlarge it so y'all can see that. Okay. I tell my students, if you thank you, Alyssa, for saying that as well. Yes, this is actually on YouTube also. If you memorize this order, get you some index cards. I've been saying index cards for 1,000 years. If you write this on your index card, when you have to write out the electron configuration for, let's say, chlorine, I know that chlorine has 17 electrons, right? Because chlorine has 17 electrons, right there, all I got to do is count up until I get to 17. So if I count this up, I got 2 plus 2 plus 6, that's 10, plus 2 is 12. I need 5 more. But rather than writing 3P6, I'm going to erase that and put 3P5. This is another cheat code that you can use. So if you know the number of valency, the number of electrons, excuse me, if you know the number of electrons you need, you just count up until you get to that number. Until you get to that number. So let's say I needed, let's say 8, because we were dealing with oxygen previously. Oxygen has 8 electrons, right? Well, let's count up to 8. 2 plus 2 is 4. We don't need 6. How many more do we need right here? We needed 4 more. You're not going to write no more of this part right here. We're going to actually delete that part off. So we would write 1s2, 2s2, 2p4. And if you add up those superscript numbers, that's going to give you your 8 electrons. But also remember, I said, if you know where oxygen is located on the periodic table, it's in the P block, it's in the 4th one. This tells you the last thing you would write for your electronic configuration. Okay. Alyssa, you want to pick an element. We'll do one together. That way you can kind of see the pattern. So pick an element and we'll do it together. Now, and while you pick potassium, okay, potassium, we got you. Well, Monique, it's It's all good, honey. It's all good. And Dina, you said silver. So we'll do those two. We'll do potassium and silver. Well, you know what? I'll say this representation matters. Okay, I will say that. Sometimes if you have a female professor, if you have a male professor, if you have a professor from your native country, let's say you, and look, when I was in college, my professors were they were Indian and African, and they had thick dialects. And me being a young person, I didn't want to understand them. I didn't want to take the time to understand them. So I suffered a little bit as a result of that because I was being ignorant, didn't want to do anything because I was like, okay, I can't understand them. Fast forward, they had theirs. They already had their degrees. So I had to do what I had to do to get through their dialects. So I will say representation does matter. When you have someone that identifies with you, sometimes you embrace the information better. Yes. Most people in STEM are, people of color, like your Asian people, Indian people, African. So, yes. I'll take that as a compliment. Okay, so we've got potassium. Okay, we're going to do potassium. Now let's find that on the periodic table. Okay, so here is potassium. Let's zoom in right here. Let's get these questions answered out the way. Let's move this out the way too. Here we go. Okay, potassium. Yeah, learn chemistry. My YouTube is Learn Chemistry with Professor TK the Chemist. And if you go to the LINK in my bio, it'll take you straight there. And this is being recorded. Yes. Potassium is in what group? Or I'm sorry, what block is potassium in? Okay. Thank you, Dina. Yes, group 1 S block. Thank you, Monique. You're welcome. Okay, yes, it's in the S block as in Sam. It's in the first one, so S1. It's in period 4. So you put that together, you got 4S1. That's the last thing you're going to write for potassium. Oh, but we can't forget, how many electrons does potassium have? Now, I know y'all can't see this on the chart, but I'm just going to tell y'all it's 19. Okay, 19. So if we go back to our little thing here, okay? If we go back to this part right here, let me zoom out a little bit so y'all can see this. Yes, Monique, that's right. Period block group. Honey, that's right. There you go. That's right. That's right. Now, I'm going to erase this so it won't be a distraction. Okay. If potassium has 19 electrons, it was in the S block. It was in the first one, the 4th energy level. 4S1 is the last thing you're going to write. So guess what? We're going to write all of this out, but when we get to 4S2, we're going to replace that with a 1. So we would write out 1S2, 2S2, 2P6, 3S2, 3P6, 4S1. And if you add all those together, you will end up with 19 electrons. 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 1 more gives you 19. And there you have it, 19 electrons. Now, the other request was silver. Silver has a lot more issues because guess what? Woo! Silver has 47 electrons. Now, what we ain't gonna do, and yeah, I said ain't, we ain't getting ready to write all of that out, but what I will do is show you how to get the right answer. Because it's long, y'all. That's a long one to write out. Okay? But let me show you where silver is. Yes, we could write the noble gas configuration for it. Yep. And speaking of that, Alyssa, since you said noble gas, let's talk about that. No, what noble gas comes before potassium? So if we go back to our periodic table, do what now, Monique? What are you talking about? So the noble gas that comes before potassium is argon. So argon would take up 18 of those electrons right there. Okay. It would take up 18 of those. So we would end up writing argon in brackets and then 4s1 on the outside. That would be the abbreviated version. Okay, now the one that's long. Oh yeah, I know what you're talking about. She done call it a Christmas tree, but you know what? You're on point with that one. I kind of thought that's what you were saying, but I didn't want to say the wrong thing if that wasn't what you were saying. So this is what she's talking about. I think. Is this what you're talking about, Monique, right here? Now, those of y'all on YouTube, you ain't gonna be able to see this because I got my camera off because I look like, say, what now? That's what I look like. So y'all ain't ready to see me right now. But on YouTube, without, oh, you say no without the blog. Okay, you hold on for a second. Okay, you hold on. Now, I'm gonna show y'all the answer to silver. Okay. So that way you can see how long this is. Let me see if I can find it. Yeah. So silver is in the it's in the fifth period. Wait, okay, it was in your notes. Was it on this part right here, Monique, or was it on the purple notes? Which ones was it? Oh, okay. Let me. Okay. Hold on. I think you're talking about this right here. Is this the page you're referring to? Okay, gotcha. Okay. So yes, so right here, this is the order that you fill them up. And silver is in the and I'm gonna show again, YouTube, you can't see this, but if you go to your periodic table while I'm saying this, I'm gonna show y'all here, right here. You see here silver, okay? And it's in the fifth period. Aicha, it depends, or that depends on what you already doing right now. I gotta talk to you to know more about your study methods in order to answer that question. Okay, but yeah, so silver is a part of that group. Well, honey, you gonna answer your own question, okay? You answering your own question. Silver has 47 electrons. So you would go in this order right here. It's in the fifth period. And because it's in the fifth period, it would actually stop. Let me see. Hold on. Yeah, it's gonna stop somewhere right here at the 5p section. So that one is a little longer. But what I will do, okay, what I will show you, just so you can have an idea of electronic configurations and how long they can actually go. Yeah, it's actually, I'm sorry, it's going to stop in the 5D section, 5Ds. Yeah. Because it's in the fifth period, It's down here with the D's, and it's in the D block. Okay. Now I'm gonna see that right there. It's in the D block. And because it's in the D block, it's in the fifth energy level. That's why I was saying it's going to be in the D's. So yeah, you have to write all that down. Oh, it goes far. It goes beyond 7P. That's for sure. And at that point, chemistry, it's pointless, in my professional opinion, to even do electronic configurations beyond that. That doesn't even make sense. I'm just saying. Okay. Now, I know we had some more requests, okay? And look, it's 1:25, y'all. Oh, Lord. I didn't realize I was on here that long. Let me go back to where we were over here. So this was the other thing. We did the orbitals kind of sort of identifying oxyanions and naming ionic compounds are pretty much the same thing. So I think this was Asia's question. Asia, are you still in here? Hey, Tasia, hold on for 1 second, honey. Yeah, hold on. Asia, I think this was your question. Are you still in here and you want to know about naming ionic compounds and oxyanions? Are you still in here? You're welcome. Asia done dipped out on me. Because she ain't saying nothing. Okay, let's go. Okay, it's the person that want to know about empirical formulas. I think this was the same type of question. Okay, now listen. Okay, so let me do this. Let me go ahead. Look, Taisha, you just stepped in the building right on time. I'm gonna close it out with you, okay? I'm gonna close it out on you, and you want to know about wavelengths. Okay, I thought I did one of these before, but that's okay. So YouTube, you all won't be able to see okay, you said you always get the symbols confused. Okay. Hey Monique, yeah, wavelength is also in chemistry. And how is because we're talking about energy. And when you talk about energy, E equals, this is the formula right here for energy. E equals H times that little funny shape V, which is the frequency. You can also rearrange this formula two different ways. And I'll show you how to do that. Now, Tasia, what chemistry class are you taking right now? No, this isn't for, well, it's sort of heat. Okay, General Chem 1. Okay, I got you. So, excuse me. So for these types of problems right here for energy, okay, E equals H. I was trying to find one that I could give you with the frequency. Oh, yeah, here we go. And then you could also use this right here equals lambda times that little v right here. So I'm going to give you all several different formulas that you can derive out of one, okay? That little funny shape T, that's the wavelength, okay? And this funny shape V, that's equal to the frequency. Now, you can easily take this formula right here, E equals H, which is Planck's constant, times that little funny shape V. And I can actually rearrange this formula to give you, I'm going to put an or over here, E equals H times C over that little funny shape T. Okay, yes. So you want to know like the units. Yes. Hertz. Yes. Yes. And you can, yeah, you can use those many different ways. You can use the units in many different forms and different fashions. So yes, and I'll show you that too. So let's say, let's see here. Suppose I say, give me the energy. If I tell you Planck's constant, that's 6.626 times 10 to the negative 34 joules. 6.626 times 10 to the negative 34 joules. I think joules per second. Hey, we already did Aicha. I don't know if I'm saying your name right, but this is actually on YouTube. So you can actually go through there on YouTube because we already did that. We actually did a whole 30-minute lesson on Lewis structure. So you can go to my YouTube channel after I end this live. You can actually go over there and get a copy of this. Yes, that is correct, Monique. Yes, yes. So then if you got your wavelength, okay, which is that little funny shape V, or your frequency, excuse me, your frequency, the frequency is actually equal to like per seconds right here. It's like 1 over the seconds. So when you end up canceling those units out, you'll end up with joules as your final unit answer, okay? You'll end up with that. So here's what I need to do. Let me find one. I need to find a problem because I don't have one in my notes that I can just pull for you. So let me go ahead and see if I can find one real quick. Okay, so give me 1 second. Let me see. I'm just going to pick an energy problem that I can just let's see for chemistry. Let me put for chemistry so that way they don't give me let me say wavelength too. Oh yeah, see, and I had said joules per second. Yeah, it's joules seconds. Yes, joules second. Let me find a problem that I can do. Do you have a problem that you can type out? And I see one right here that I can do. I'm gonna choose these two right here. Okay, and I found one that I can use right here. So okay, so I found one. Okay, your professor gives you handouts. Good, 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 good. But look, that's good because some professors don't even give extra notes. Okay, so I just took this real quick because I didn't have any I don't have a worksheet that I could do with this, but I just found this for you. So I'm going to actually write this out. Okay, good. When do you plan to apply to medical school, Monique? Okay. So here's what we got right here. Okay. This is your equation, which is what I showed you before. Okay. You got H, and that's a funny shape V. That's for energy. Then you've got your speed of light, which is equal to the frequency times your wavelength. This is Planck's constant, and then that's the speed of light right there. So here are some examples right here that you can follow, okay? And we'll do one of these problems so you can make sure that you got this down pat. Oh, okay, Monique. Okay, I got you. I got you. You know what? It's all good. You're gonna get in. Thank you, Ken. That's right. Fun and chemistry in the same sentence. Yes. Ah, okay, so calculate the wavelength of a photon with with energy of. That's right. You got this, Monique. That's the one thing I can say. You don't give up. You do not give up. Do not give up. So for this problem, they're asking you to find the wavelength. Well, guess what? This little funny shaped V right here is the symbol for the wavelength. And we're going to rewrite this formula out so we can find out. Whoops. That's frequency. Hold on. So you remember how I put on the other page, you can also say E equals H times C over that little funny shaped T right there. Well, here is the formula right here, okay? And I'll do that one next, Taisha, I'll do that one next. So to find your wavelength, it's gonna be equal to H times C over E, okay? So this is what we got right here. I'm gonna scroll down a little, so yes. There we go. Okay, so what we're going to do, we're going to put Planck's constant number, which is 6.626 times 10 to the negative 34 joules dot seconds, times the speed of light, which is 3.00 times 10 to the 8 meters per second, divided by the E, the energy that they gave us up here initially, which was 2.0 times 10 to the negative 19 joules. 2.0 times 10 to the negative 9 joules, okay? So what are you going to do? You're going to plug these numbers in, okay? And when you plug them in, first, let's go ahead and cancel out our units. We don't need the joules here. Those are canceling out. We don't need the seconds either because those cancel out. So you're left with your wavelength in meters. So you multiply these two numbers across, 6.626 times 10 to the negative 34 times 3.00 times 10 to the 8th, then divide that by 2.0 times 10 to the 19th. And your answer will come out in meters. In this problem right here, if they did not ask you to find it in nanometers, then you can keep the answer in meters. If they tell you to put your answer in nanometers, then all you have to do is convert that accordingly, okay? So if your final answer comes out in meters here, to convert that to a nanometer, you would just have to multiply by the correct conversion of knowing what 1 meter equals to in a nanometer. So your question is, a photon has 6.6 kilojoules of moles of energy. What is the frequency of one such photon in hertz? Okay, so you're converting the kilojoules to a hertz. Okay. So let's go back up here. Okay, so what's the conversion from a nanometer to a meter? Okay, so let me show you. Let's see right here. For a nanometer to, because what I tell my students to do, I actually move the decimal over because it takes too long to do the conversion part. But for students that do it the dimensional analysis way, whatever this answer is, 1 nanometer equals, I'm sorry, 1 meter equals 1 times 10 to the 9th nanometers. So if you had to put this answer in nanometers, you would need to know that 1 meter is equal to 1 times 10 to the 9th nanometers. Okay, so all you would do is take whatever answer you get here, divide it by 1 times 10 to the 9th. Okay, so to go back to Taisha's problem, she says a photon of 6.6 kilojoules. So let's write that down. Okay, 6.6 kilojoules. What is the frequency in hertz. Okay, so for this problem, first thing you need to do is convert the kilojoules to a joule, okay? And do you remember how to convert a kilojoule to a joule? Do you know that conversion? Right, divide by 1,000, that's correct. So 6.6 kilojoules, okay, times. So if I put right here, not divide by 1,000, okay, because you're trying to get to a joule, you're going to put 1,000 joules on the very top, okay? So you're going to get rid of your kilojoules right here, all right? Then to get to that hertz, because that's the final step right there, we're going to use our formula over here. Remember how we said E equals H times that little V, and they're asking you for the frequency? Yep, 8 kilojoules on the bottom to cancel out. That is correct. That is correct. To get your frequency, because that's what the question was, you want to know what is the frequency, okay? The frequency formula is equal to E over H. So you're going to take this number up here. So 6.6 times 1,000 gives us 6,600. So you're going to say 6,600 joules divided by Planck's constant. 6.6. Let me write that. Y'all see how big I write. Let me put that on another line. Sorry, y'all. Hold on. Okay, so right here, E equals, I'm sorry, V, that little frequency symbol, okay, equals E over H, Planck's constant. So 6,600 joules divided by 6.626 times 10 to the negative 34 joules dot seconds. That's right there. When you cancel out your joules, that's going to give you seconds negative, which is also the same thing as a hertz. That's what that's equal to. So once you put this into your calculator, I don't have my calculator nearby, but if you plug that in, 6,600 divided by 6.626 times 10 to the negative 34 per second, that's going to give you your answer in hertz. Okay, guys. So yes, I've been on here for almost 2 hours. Woo! I can't believe it. Seconds negative equals hertz. Yes, that's correct, Taisha. That is correct. Seconds hertz. Yes. So whenever it's written like, whenever you see it written like this, seconds to the negative 1, that is the same thing as a hertz. You are welcome. You are welcome. So y'all, I normally don't go live on Fridays. This was just a pop-up because we were reined in because of Hurricane Helene. So I decided to pop up here today to give you guys just a quick tutoring lesson on Friday. So you all, you're welcome. Hey, T, how you doing? Yes, my normal days are, you're welcome, Alyssa. My normal tutoring days are Tuesdays and Thursdays at 1 p.m. Eastern Standard Time and Tuesdays and Thursdays at 7:30 p.m. Eastern Standard Time. So yes, if you all need some individual tutoring, I will assure you, you will come away with more than what you have learned in class. Okay? You can believe that. I've been doing this for over 25 years, y'all. So give me a chemistry question I haven't seen, except for organic, because organic and I didn't get along. So don't you ask me for no organic help. You're welcome, Monique. Okay, yes, Taisha, yes. But make sure y'all tell y'all's friends what Professor TK the chemist does, okay? So guys, I am going to head off. Oh, Kalani, hold on. Oh, Lord, let me see. Hold on. Okay, let's thank you, Kalani. Let's see what's your question. How can I determine the number of atoms in 19 grams of sodium? Okay, we're going to close out on your question, Kalani. Okay. All right, so 19 grams, 19.0 grams of sodium, converting that to an atom. Okay, let me put it in black because it's hard to see. 19.0 grams of sodium, convert that to an atom of sodium. Okay, this is what you're going to have to do. Grams of sodium to a mole of sodium, then to an atom of sodium. This is a two-step process. It's real simple. It's not gonna be hard to do at all. Okay. So here's what you're gonna have to do. 19.0 grams of sodium times on the bottom, you got that molar mass that you already provided, which is the 22.99 grams of sodium. That's the molar mass. To go from a gram to a mole, you must divide by the molar mass of sodium. So 19.0 grams of sodium divided by 22.99 grams of sodium cancels out those like units. In this last step right here, we're going to put 1 mole on the bottom to cancel out your moles of sodium. And on the very top, Avogadro's number, okay, which is, look, I got all these numbers in my head. 6.022 times 10 to the 23rd atoms of sodium. And all you got to do now is plug that into your calculator. Grams to moles to atoms. Yes. Taisha, is moles, molecules and atoms are technically the same thing. So if this question would have asked you about molecules, you just replace atoms with the word molecules. And I don't have my calculator near me, but you just multiply 19.0 times 6.022 times 10 to the 23rd, then divide that by 22.99, and that will give you your answer. Okay. So I hope that was able to, answer your question, Kalani. They are, Taisha, they are, they are atoms and molecules. Okay. To keep it simple, as we say, KISS, keep it stupid simple. You're welcome, honey. You're welcome, Kalani. You're welcome. Molecules and atoms can be used interchangeably when it comes to setting the problem up. Molecules and atoms can be used interchangeably when it comes to setting the problem up. So rather than going down that rabbit hole of breaking it down further, you just keep it simple. They mean the same thing. Like tomato and tomato, potato and patata, or pop. Y'all say pop up north and out in the Midwest, but down south we say soda. So soda and pop mean the same thing, just like the atoms and molecules, okay? They mean the same thing. Well, okay, good. Okay, Kalani, you got that? Okay. Well, the thing is, you say you feel like it will confuse if you use interchangeably. Well, listen, if I go up north and I say I want some soda, well, I hope everybody would know that I mean pop, because down south, that's all we know. We say soda down here, but up north and in the Midwest, they say pop. But we know that they mean the same thing. Okay, New York, y'all say soda. Okay. Yeah, well, I thought the Chi-Town said pop. Yeah. Oh shoot. Okay, but Tasia, let me say this though. That's right, it's both though. If the question says molecules, you need to use the right unit though in that answer for those. Look, y'all must be young folks that's saying y'all have never heard of pop. Y'all go Google. Go Google the vernacular for what you say. If you're in the Midwest and y'all say I want some soda, see what they say. If they say pop. Okay, guys. Well, I appreciate y'all for joining me on this Friday. But now you calling me old. Oh, now, Ty, see y'all. Look, you see what Ty just said. Ooh, let me in your comment. Cause see, that's why you got that one wrong. Okay, let me pin your comment. You're welcome, Tylen. Hey, girl, how you doing? Tasia, molecule is not the same as a mole. Okay, they are not the same. We are not the same. Okay. Molecule is just like saying Drake and Kendrick are the same. They are not the same. Molecule and mole are not the same. Cardi B and Rihanna are not the same. Okay. Yeah, but there's no abbreviation for molecule. You gotta write the word molecule out. Now, the abbreviation for a mole, like if I say I have 5 moles of something, the abbreviation for that is MOL. I'm like, why do we just take the E off? I know, right, T. So you told your professor that it was too much to write out, and rather than writing out the entire word molecule, you decided to write a mole. That's like me saying I thought Drake was the same person as Kendrick. Negative. I thought Tupac was the same thing as Biggie. Negative. I thought Beyonce was Riri. No, they are not the same. They may seem, they may sound alike, but they're not the same. Well, Monique. Okay. Redox, listen. I've been on here for 2 hours. So Professor TK, the chemist, is tapped out. I'll be back on Tuesday, though. Okay, I will be back on Tuesday. Oh, and let me go ahead and stop this on YouTube.